zk. However, we're dividing that vector by the square root of x squared plus y squared plus z squared. If we think about it for a minute, this is just the magnitude of this vector. So that this is a unit vector. We're going to divide at a given point. We can think of the position vector rooted at the origin divided by its magnitude, which is going to give us what? It's going to give us a vector in the same direction, but this is going to be a unit vector. So that if we have another point, let's say closer to the origin, its position vector is smaller. If we were doing this field here, we see that that vector ends up being smaller. But in this case, we're dividing the vector by its magnitude, getting another unit vector. So if this represents a unit vector, then this vector is going to have to be of the same magnitude. And if we have a vector way out here whose position vector would be bigger than either of these, and whose vector in this example would therefore be greater, that unit vector is going to be of the same magnitude as all these other vectors. So that our vector field, if we just make a few more points, is going to be such that it's always of the same magnitude and it always points away from the origin. No matter where we go, well, I'm not getting the direction right there, the vector will point directly away from the origin, and you can imagine the whole plane filled with vectors of this nature. They would appear to be moving out from the origin. They would all have the same magnitude. One more example would simply be the field that we would get by instead of dividing by the square root of x squared plus y squared plus z squared, let's just stick with our same original vector. But let's now do f of x, y, z equal to xi over the quantity x squared plus y squared plus z squared plus yj over the quantity x squared plus y squared plus z squared plus zk over the quantity x squared plus y squared plus z squared. Factoring out the common factor 1 over x squared plus y squared plus z squared, we get this. This is no longer a unit vector as it was in the preceding example, because now we have a denominator that's actually equal to the square root to the square of the previous denominator. Now, I'd probably leave it to you to prove that the magnitude is inversely proportional to the distance from the origin. The vector is, though, in all cases, directed away from always the origin. This, because of course this is just a constant multiple, or a multiple, not a constant multiple, a multiple of xi plus yj plus zk, which is our, essentially we call that our radial vector field. So the vector field is radial and of magnitude inversely proportional to the distance from the origin. And if we wanted to sketch that field, and let's see, this marker's misbehaving. Okay, if we wanted to sketch that field, we could sketch it at a number of points. And the closer it is to the origin, the bigger it is, but it points away from the origin. The further it is from the origin, the smaller it is, but it points away. So that we might get a field that looks something like this. Okay, well, let's go ahead and sketch just a couple more points. Not sure that I'm getting all these of correct relative sizes, but we get the idea. It's a vector away from a field away from the origin of decreasing magnitude. And we could, if we wish, draw circles around the origin. Not a very good circle. But the vectors on this circle would be perpendicular to the circle, radial away from the origin, and larger than the vectors on this circle, which would also be directed perpendicular to the circle and away from the origin, but would be of smaller magnitude. Not all vector fields, of course, are radial, but we can use these as some typical examples, and we'll see many more examples of vectors that are radial multiples of xi plus yj plus zk.